Right. Hello, everyone. This is the fifth recorded lecture of Introduction to Complex Analysis and also Riemann surfaces theory. Today is already April 5th. This is the fifth lecture. So not as the usual undergraduate or even graduate level of complex analysis lectures, I'd like to focus on at least the application to the side of Riemann surface theory, especially the Riemann rule theorem. So in order to do it, I try to put some the effort to just polish the structure of this sort of lecture and the settings of the complex analysis so far, such as proving identity theorem, open mapping theorem, and so on and so on. So from today, I'd like to talk about the important the property of the holomorphic function defined on compact Riemann surface. But before we start, so even I already mentioned this already. However, still it is safe for all of us to start from the definition of the metamorphic functions. So the metamorphic functions that turns out to be okay to call it by holomorphic functions from now on is the following. So the setting, so we will focus on compact Riemann surface. And briefly writing. So from now on, let me simply just write compact Riemann surface in this way. So we will call the function a function f from x to c, including the infinity, is metamorphic. Of course, there are several equivalent criterion, but let me just give the simplest possible the statement. So this is the case for any point that we choose, we are able to write a given function in a small neighborhood. So this can be written as g over h, and where h evaluate p should be non-zero, and g and h are holomorphic. So this can be taken as a definition of metamorphic functions. So especially, so we require, so remark, since X is compact, since F is compact. So if we investigate either the zero set or the set of the poles, so we know all those the points are isolated. It follows from the identity theorem from the exactly previous lecture. So we can see that each non-zero metamorphic function has at most finitely many zeros and poles. So because isolated the set which is discrete subset inside of the complex set, it must be finite. So here a little bit like the trying to being rigorous is the codomain of the metabolic function. So of course, this is the rigor. It turns out to be rigorously okay to simply say, well, we'd like to just add the point at infinity to create in fact, the two-dimensional sphere from the perspective of one-point compactification for sure. But there's also a way to describe it in terms of the CP1. So let me just mention that when we say CP1, this is one-dimensional complex projective space over C or projective line. This is defined as C2 excludes 0, 0. take the quotient by the following relation. Each x comma y are related by lambda x lambda y, where this lambda for some lambda which is non-zero complex value. So this can be taken as a definition. So each of the non-zero like the vectors pairs x comma y, so we allow to multiply by non-zero like the scalar, so that naively speaking this is the equivalent class of the direction of each of the vectors. So for this like the quotient set, so it would be reasonable to just denote by this like the notation of the equivalent like the class, and we can say that either x should be non-zero or y should be non-zero. Of course, this like the notation of a bracket, x versus y represent the equivalent class coming from this like the equivalent relation tilde. So it is like the also reasonable to denote two so-called the affine open subsets. So for this one, so we require for each like the point inside of the CP1, for example, we require x to be non-zero, and for u1, we can also require the similar condition to the second, like the component. Then why this, like the description of CP1 is indeed useful. So the reason can be followed from the simple like the argument with the definition of CP1. So we can see that if we take arbitrarily like the point from CP1, then there are two possible like the choices. There are two possible choices. If x is non-zero, namely this point is the element inside the U naught, then you can see that this can be identified as 1 versus y over x. And if y is non-zero, of course, there should be possible overlap for sure. However, still, we can consider either of two scenarios. Then this can be also written as, so let me just erase this like the two, like the overlap of equality, so that we can just make the y component to be 1, and it becomes x over y. And in this way, if we write y over x as just a z, which is clearly C value, then x over y should be written as a 1 over z. So if we regard z as a local coordinate center at the origin on the complex plane, this, so if we have a 0, and from here we use this complex plane to locally write the coordinate by z, then the usage of the 1 over z should be represented by the 1 point at infinity, so that if we just glue by this just a 1 point from like the C1, so that you can intuitively see that it makes the so-called Riemann sphere. That is usually also written also by S2. But so you can see that this like the infinity, this point should be written by to 1 over z, so that the rigorous description of the CP1 indeed represent the one complex plane adding by one additional point, so that we now have this like the intuition. Of course, we are able to establish the explicit bijection between CP1 and S2 for sure, but I will not talk about it during the lecture. If you are interested in it, you can try to either establish and just search from all those like the known like the literatures. Now, so what you can see is that we are also able to replace this part by CP1 as you if you want. So why this is indeed like the useful. So even we said, sorry. So I made a little bit like the important, actually this is an important like the mistake. So I should say I should say the codomain of metamorphic function should be just nothing but C1. So in this like the perspective, infinity is the point that we are not able to define in general. However, once we now at the point at the infinity on this codomain, so now we have a hoop to instead of call this function by metamorphic function, we are able to call it by the holomorphic function. So now let me just mention that as a proposition. So I do not know how many propositions I need to put today. So let me put this as a proposition one so that if necessary, I can just cite this like the proposition. So there is one-to-one correspondence between. So one side is nothing but the function that we already considered. So if you have a function, say g from x to c, that let me require this G is metamorphic. And for without like the mentioning on this like the space X, X represent compact Riemann surface. Otherwise, uh, I should clearly mention this like the space. So G is a metamorphic function, and we are also able to link associate to the function from X to CP1. That is, F is now holomorphic. So why this like the proposition is useful? As we know from open mapping theorem, so if we require the any holomorphic map defined on a compact Riemann surface, that meaning that the it implies holomorphic function, it maps to C, so the codomain is C. In such a case, open mapping theorem tells us that such a function must be constant, so it is natural to add by the infinity at by just infinity point. So this is something very natural, and at the same time, it is just equivalent to actually use actual any metamorphic function. So of course, we are able to use the rigorous definition of CP1, but let me just provide a proof which might be a little bit more intuitive. So if you use the like the infinity, so infinity is not the like the undefined point, but now we have a way to describe this infinity. But still, let me just use the intuitive like the description. So in order to just define the one-to-one correspondence, so we can simply directly start from define such a like a bijection. So now we have a map, and let me start from the holomorphic function from x to CP1. That is f is holomorphic that maps to metamorphic. So that we just need to establish such a like the map in the following way. So as follows. So B evaluate any holomorphic function. So we'd like to define this as a metamorphic function whose domain is complex plane. So if we plug in any point from compact Riemann surface, so there should be two possible like the choices. So either f maps to infinity, or sorry, if f does not map to infinity, or if f maps to infinity. So by the way, so as we already just established, for example, this guy by z. So this guy is now 1 over z. So it is just a natural. If you wanna just use this like the infinity as just the rigorous like the point. For example, you can just use, for example, 1, 0 versus 1. So that this is same as nothing but 1 versus 1 over 0. So that we just treat this as a infinity. If you want to replace this like the infinity point by the point at the CP1. So anyhow, so let me just use this more like into like the description. So if f of z is not infinity, so then it is clear that we can simply just use the same function value. Otherwise, we can simply use infinity as well, or the point of like the equivalent class of 0 versus 1, as I already mentioned. So but anyhow, so here the important like the point I wanna mention is that so this like the pole should not be thought as a pathological singularity. This is concrete like the point on CP1. So this map is well defined. So now let's try to just observe that F is holomorphic. F is holomorphic. So that still we can use our previous like the propositions that we already established, such as like the identity theorem, open mapping theorems, and so on and so on. So that this forces that if we collect the point from the compact Riemann surface, that makes f of z to be infinity. Okay, this is not pathological singularity any longer. So this must be discrete. So the argument must be the following. So identity theorem tells us that all like the point that maps to infinity should be isolated. That's what identity theorem tells us. And once it is discrete, like the set inside of the compact subset, that by using the compactness, so it must be finite. So from here, so now we can see. So because of this, like the reason, so we are able to write down for each of the point of the function. So we need to check whether or not this function should be written as a holomorphic function over H, but there are only like finite, like many just a point that makes the pole. So by using the definition of the pole, we are definitely able to make the ratio of two holomorphic functions. So thus, B of F must be metamorphic. So the way to check is for finding many like the points of the poles, just use the information of pole to write down as a pole like the order times this function is holomorphic. So if you divide it, then it satisfies this like the definition, and we just need to repeat finally many like the points of the poles. Otherwise, it's just nothing with holomorphic function. So it's easy to check. We want to say this like the map is bijection. We want to say this map is bijection. Why this map is bijection? First, we need to see whether or not this map is one to one. So if we choose different two these distinct two Holomorphic functions, then it's clear that so the corresponding like the function values by this map B must be like the distinct. So it is clear that big phi of f is one to one. So it just follows from this definition of the one-to-one map. Distinct two points in the domain maps to distinct two like the points of the codomain. So we need to show this map is surjective. So let us take any metamorphic function from x to c. So that now we just need to associate polynomial function that maps to this like this guy. So because there this is holomorphic like the metamorphic function, so there is a so that we are able to consider a set of poles as of G such that so if we just restrict to the like the domain outside from this like the set, then this map now becomes holomorphic. That's the definition of a metamorphic function. And again, the set of poles on the complex subset are isolated, and thereby it must be the finite set. It must be the finite set. So we just need to extend this function to be CP1, is CP1. So it is now very like the clear that we can simply just extend the codomain. So it's just nothing but the same assigned to the same value. Then let us just define the map this way. Then clearly this map is holomorphic. Then what we just need to do is we need to just fill the gaps of those finitely manifold points of the poles. Why that could be happen. So what we know is so we are able to use the like the local coordinate such as like the 1 over z. So if we just use the like the map to control each point of poles, then if we use like the phi composed by this f, phi composed by this f. So then this is bounded at each pole. So now we have a holomorphic function at the puncture like the small like the neighborhood. Then it is bounded. Then we can apply Riemann removable singularity theorem that we also already proved from last like the lecture. Riemann removable singularity theorem. So that this extends unique map, not just from X, like the outside of X S to CP1. Now we have F X to P1. And we can throw this part away so that now we have just a map F, which is holomorphic. And it is also clear this is unique like the extension that satisfies this desired condition. Because there's just the only way to fill this like the gap, fill this like the gap, and G is the desired like the map to satisfy because at the like the pole it maps to the infinity without using this like the small like this V. So it just completes the proof. Okay, so now we are ready to use the each of the matter function as just nothing but the holomorphic function. So this like the feature of the holomorphic function defined on the compact Riemann surface is very like the beautiful like the implications that is so behind like the structure of the holomorphic function on a compact Riemann surface is in fact it turns out to be so-called the covering. So now let me try to cover the necessary concepts of the covering maps. So of course this is a concept of algebraic topology, but still this is really like the needed. So because this like the explains why like the complex analysis naturally like the links to the topological like the word. So let me just start from the necessary like the definitions. But before we talk about the setting of Riemann surfaces, let me just restrict the setting to be the topological manifolds for a moment. So topological manifold just means it's a locally like the Euclidean and it satisfies certain topological axioms, but it's just more like the general classes than the Riemann surfaces for a moment to explain this like the concept covering map. So let pi, the map from M tilde to M. So this is let us assume this be a local homeomorphism between two topological manifolds. So that's the assumption. So we'd like to say this map pi is a covering map. This map pi is covering map if it satisfies the following. So for each like the point from the codomain, if point out the codomain, so we are able to by the way covering map also requires the like the surjectivity. So we are able to find a small neighborhood V of X such that so every like the connected component of this like the inverse image is homeomorphic to V, of course, by this map. So that's the definition. That's the definition. So one like the good like the example is like so if you have a map from R1 to S1, so that each of the point you can assign to e to the say 2 pi it. Then it is easy to imagine that the base is like this, S1, and we are like the winding the wire to just go from like the initial some of the like the initial like the stage to goes forever so that if you choose any point then you are able to find small neighborhood so they each of the like the inverse image should be like this and each of the connected components are clearly homeomorphic to the like the prescribed like the like the neighborhood B. So that's the some like the intuition. So so also there are some like the terminologies. So we say the inverse image, let pi be a covering map. Then, if we just consider the inverse image of only just a single point, this is called a fiber at this point. So that the fiber in this, like the previous example, is like this. The collection of all of them are called by the fiber. And also, each of the like the connected component in the inverse image is called the sheet. So the connected component of pi inverse b so is called the sheets of B. So those are also very important. Like the terms use many like these different like the places, of course, including topology. So you can see that this is the first like the sheet, this is the second sheet, third sheet, and so on and so on. And these are the fiber at point X. So now we wanna investigate some important like the like a proposition that will be applied to the holomorphic function on a compact Riemann surface. So this proposition is important. So let me just now state this proposition first and then try to explain the proposition two. So I'd like to establish the criterion whether or not given map is covering like the map. So in order to do it, so let me start from certain surjective map. So f from m to m tilde, m prime to m be surjective. And of course, we are talking about topological like these spaces. So all maps we assume should be continuous for sure. Continuous map between two topological manifolds. So that's the setting. So we assume few things. Number one, this map is a local homeomorphism. So you can investigate whether or not each of the conditions are satisfied by the covering map. If you just look at the picture above, so local homeomorphism just means that we are able to find a small neighborhood so that we are able to just assign from one to the other in the homeomorphic way. So that must be the definition. So this condition is definitely satisfied by any holomorphic or any covering map. And the second condition is a little bit subtle. So we require for any compact K in codomain, we take the inverse image. So this guy must be, of course, this is in M prime, but this is also compact in M prime. So this, like the second condition, has also the name on the map. So we simply will say F is proper. We said we say F is proper if it satisfies this condition. So this condition looks quite like the subtle, but we should require this condition as well. So once we require these two conditions, then F must be covering map. So moreover, once we achieves the covering map, so we also get that each of the fiber must be finite. So that let me now provide the proof of this like the improper like the proposition. So proof like the should split into several like the pieces. All right. So let us proceed the proof. So let us try to see the last like the sentence why each fiber must be finite. So let us just observe that each like the singleton set in M is clearly compact. And by the assumption, so this like the inverse image, this inverse image. So it must be compact. So this is compact. This must be compact. So we'd like to claim this guy must be discrete. Why it should be discrete? So let us take any point from this like the fiber, from this fiber. Then we didn't use the assumption of the local homeomorphism. So by using that condition, since F is local homeo, so we are able to find small neighborhood in M prime. So such that, so if we restrict this function to use of P, so from this open set to the image, so we know this guy is homeomorphism. So in particular, so this forces that such a like the this like the map must be one to one. This map must be one to one. So what that means is that so this user P, this like the user P, contains at most one point of the fiber because it is homeomorphism. So there is no way to map from this neighborhood to X except the point P. So this means each point is isolated. Or I should say, each point of this fiber must be isolated. So once it's isolated, then it just means the discrete. And now we are done because so we just need to combine compactness with discrete like the set forces F inverse X. The fiber must be finite. So the first part, like the last like the sentence is already proven by this like the argument. So now we need to prove F is a covering map. So now what we know is the definition of the covering map. So what we should see is that so whatever points that we choose, then we should be able to find a small neighborhood such that each connected like the component of the inverse image should be homeomorphic to the like the chosen like the neighborhood. So that's what we need to show. So in order to prove this like the F is covering like the map. So let us take any point from codomain. So let us choose from M. Then what we know is because we already established that each of the fibers is finite. So let us just write F inverse of X, the fiber, consists of say R numbers of the elements in M prime. So we know this guy. So what we know is F is, so we can still keep using those two assumptions. So since F is a local homeomorphism, so that we are able to find small neighbor for each of these, like the point of p sub 1 to p sub I. So for each like the point k from 1 to r. So we are able to find like the small neighborhood, let me say u sub I, u sub k, so in M prime, such that F restrict to this like the u sub k. That means from say u sub k to let me call v sub k is a homeomorphism. So now we know this guy, and if necessary, we can shrink each of the finitely many this u sub k to make this each of the open set u sub k, u sub 1 to u sub r are all pairwise disjoint. So if necessary, we can shrink each of the u sub r 1 to u sub r so that we may assume that so each u k are pairwise disjoint. Pairwise disjoint. So from this like the chosen like the sets, now let's just make the target like the neighborhood for the this like the covering like the map. So we need to choose this neighborhood. So in order to do, we will prepare. So let us simply just set not the answer yet. So let's just call it by V naught. So V naught is just nothing but taking the R intersection of all those like the sets, say B sub k. So then let's just take the all of those like the intersection, and this is just finitely many like the intersection. Still, this is open set. Still, this is open set, and it is also very clear that this like the B naught contains the fixed like the point x. So this is also okay. Sorry. So it does not contains yeah, it contains this X for sure. So now let's just use the assumption on a topological manifold. Topological manifold must be locally like the compact Hausdorff. So since M is locally compact Hausdorff. So what we can do is we are able to find also small neighborhood. Now this is our answer of X such that X is the point inside of this V, and let's just collect all of the limit points of this V. Still, we are able to make this V closure belong to V naught. So this is just a one like the equivalent description of locally compact Hausdorff topological space. So we are able to do that, and also V like the closure is compact. And we'd like to say this is our actually answer for that satisfying the condition of the covering like the map. So what we can at least say for sure, then for each K, so if we just look at the map that maps to B, so it is natural to say take the inverse image, because what we wonder is if we take the inverse image, then there are just copies of sheets that are homeomorphic to the target, like the neighborhood. So this guy is also natural, but we should consider for each of the index from 1 to R. So that's why we will take this like the intersection. So that let's just restrict to each of this like the open set. And because f is continuous, so f inverse v is open, and u sub k, each of u sub k are also open as well. So still we can say this is homeomorphism. But still, this is not the end of the story yet, in a sense that we are still using the restriction. We are still using the restriction. So we cannot say yet rigorously, we cannot say yet that F inverse of B belongs to the union from 1 to R of those like the U sub K. So this is what we'd like to claim. So why this is not sufficient? The reason is the following. So the V naught is the intersection of each of the VK, so that you can see that these are coming from indeed f of u sub k, f of u sub k. So this is the one of the like the reason that in fact this is we take the like the inverse image after we take the image. So from the set inclusion relation, once we take the image first and then take the inverse image next, then there is no guarantee that because this like the feature is coming from the subset inside of the image, this condition is in general not satisfied because we didn't start from the inverse image in this like the consideration. Even though this like the claim seems intuitively okay, but rigorously we need to prove it because we start from the image, not the inverse image. That's why. So now, in order to establish this claim, so if we have no idea, we know we want to use the contract positive argument. Suppose not. Let us start from here. So for contradiction, let's just say, i.e., this inclusion fails. That's awesome like that. Then we can choose one point. We can choose a point of F inverse of B lying outside of this like the union. This is guarantee. So in order to control this point, so let's just take a sequence. Then we are able to find a sequence. We can choose a sequence. Let's call by Q sub n that belongs to F inverse of B outside of this like the union. And we'd like to drive the contradiction by just looking at this like the sequence. So then what we know is F of Qn belongs to V that belongs to V closure, and we know this V closure is also compact. We'd like to take the benefit from this like the fact. So Q belongs to F inverse of V closure, B closure. So, and now let's just use the fact that because this B closure is compact, and by the assumption, second, like the hypothesis, so that inverse image of the each of the compact set must be compact. So it guarantees by the assumption this must be compact. And now we have a sequence inside the compact, like a set, so that we are able to choose like the convergence subsequence. So we using the same notation, so that we may assume Q sub n, Q sub passing through the subsequence, we assume Q sub n converges to Q in some same inverse image of B closure. This is now guaranteed. And now let's just relook at the fact that so by the continuity of f. So f was a continuous function. So, and we know f of qn belongs to v, and q sub n converges to q, and thereby the sequence f of q sub n must converge to f of q. This is now guaranteed. However, what we know is so from the like the consideration of this like the v, this v is indeed coming from all those like the consideration. So we are able to shrink down this like the v because we are able to shrink down this like the v naught, this like the v naught. So because we can shrink each of the like the v sub k and u sub k if necessary. So these like the or sets are coming from the small neighborhood of this x, small neighborhood of x. So the picture, what we have is we have point x, and there are numbers of the points, so that we are able to choose p sub k and u sub k like this. So we are able to shrink V naught, and thereby we are able to shrink V as well. So that as long as we shrink this like the each of the like the V and V closure, so that we know this f of q sub n must converge to x after shrinking this V around x. There's no other possible choice. So what we are saying is the following. All points of f of q sub n lie in the same like the arbitrarily small neighborhood of the v of x. Then we also know this point Q belongs to the F inverse of the V closure. So it follows that so FQ belongs to V closure. So now what we can say is, so in particular, since V was already chosen as a neighborhood of X, inside of the evenly like the covered region V naught, so the only possible like the point of X, only possible like the point of X must be one of like the p sub I. So here we can say this Q must be the point of F inverse of X. There's no other possible choice because f of q sub n converges to f of q and also x together. And this like the v not v closure should be possible to shrink as much as possible. So the only like the possible like the conclusion is that this q must be inside of the fiber. But once we achieve this condition, we already said there are only finitely many points, say from p sub 1 to p sub r. So that now we can conclude that Q must be P sub like the K for some K. So now we can conclude like this. But once we have this condition, then now it is problematic with the following like reason. So we know, so from our construction, so we use say U sub K. So U sub K is the open neighborhood of P sub K. which is q, but we said q sub n goes to q as n tends to infinity. So that says, so there must be the index such that for the any index greater than equal to this like the capital N, so we know q sub n must be the point of u sub k, u sub k. But we said q sub n is should be not the point from this guy. So that was our like the construction. So the sequence was already selected in the beginning that is cannot be the any of the point of the u sub k, but we already made that q sub n with like our infinite many indices it should belongs to u sub k. Now this is a contradiction, and this contradiction was established by just assuming this like the inclusion of the claim is failed. So that now we establish this the claim. So once we establish this claim, then we are done. So therefore, not only saying we have the homeomorphism restrict to the use of K intersecting with B F inverse of B. So indeed now we can claim F inverse of B is in the same as use of K intersecting with F inverse of B. And now we have a disjoint union of all of them. So we can say they are equal. And once we restrict to each of the like the pieces, they are homeomorphism. So thus we can also say B is evenly covered. The only non-trivial part was establish this equality, and the proof is over. So even though this is a topological like the statement, because we are like the based on this like the proposition for understanding holomorphic functions on compact Riemann surface. So that's why I wanna still cover this very important like the proposition from algebraic topology. Now let me now move on to the like the next like the statement of the holomorphic function. So in order to talk about it, so I should talk about the ramification of holomorphic maps to make the very interesting like the statement. So I first need to give the definition. So we will say let F be a map from X to Y be holomorphic, be a holomorphic map between two Riemann surfaces. So that's the condition, and we will choose arbitrary point from X. So what we will say is the following. So we will say this point A is a ramification point. If one can write locally, as the following. So by choosing the local coordinate, so we will compose by local coordinate omega, then this can be written as a phi of z times z to the power of k, where phi eval at 0 is non-zero. So this is the expression of this like the k, and if this order k is precisely 1, then we can say this map is locally bihomomorphic. Of course, if k is greater than 1, then this map is local, not locally injective. And we also define, so if so we write this k as the order. So this k is the order at point A of this holomorphic function. So this A, as we said, is a ramification point, and we will say, so So even I already mentioned, so I just wanna just call each of like the that's like the terms. So this like the E sub A, so this like the this guy is called the ramification index. This like the A is a ramification point, and lastly, this like the function value is called either a branch point or branch value. So those terms are very likely importantly used in many different fields, such as not only topology, but also complex analysis, number theory, or algebraic geometry, like the objects as well. So now this is the main proposition for this like the lecture. So main proposition, which is the following. So we have a map from X to Y. So this, let's just assume this be a non-constant to avoid the open, like the, to avoid the condition, to apply the conditional open mapping theorem, non-constant holomorphic map from a compact Riemann surface to a compact Riemann, so between, let me simply just say between two compact Riemann surfaces. Compact Riemann surfaces. So condition is quite simple. We require non-constant like the map, which is non like the non-trivial like the map in general, and we just require x and y just the compact Riemann surfaces. Just that's it. Then the following implications hold. Number one, this f must be surjective. Number two, so for each of the point from the codomain, fiber must be finite. Number three, so the number of ramification points is finite, meaning that the points that makes the ramification index is greater than equal to 2, not 1. So the number of ramification points on X must be finite. So let us say if S inside the Y is the set of like the branch like the values. So then, so if we just remove this like the set of branch like the points, then we can also look at the complement of this like the inverse image with the same map. Then this map is a cover map. Now we use the covering map, the like a statement, and moreover, so when we have a covering map, then we can talk about the degree. We can talk about the degree because even it cover like this maps, so this like the R means the degree of F. So if the degree of this covering is say n, and if you take the inverse image of the arbitrary point, and we know by the second like the implication, we know this is finitely many, there are only finitely many points, but let me call this is consists of from x1 to x of k. Then, then we will look at the ramification index of this function and taking the summation from 1 to k, this coincide with n. So we can simply say with the multiplicity, it coincide with the just the degree of this like the covering map. So let's just prove this like the main proposition. So prove. So first one, almost automatic. So we know open mapping theorem forces f of x must be open. And at the same time, x is compact. And we know this guy is also compact. And that forces issue is closed. And we are only talking about the connected Riemann surfaces. So the first, like the consequence follows immediately once we just know the statement of open mapping theorem. There's a second like this statement. So we know F inverse of Y so is compact. So why this is now guaranteed? So what we'd like to say is the following. So at least, so the fiber is closed in X, which is compact because F is continuous function and singleton set is a closed set. So that forces F inverse Y is compact. So we'd like to claim it is discrete. So why we can say that? So if we have no idea, we need to just use the contrapositive argument for driving contradiction. So if not, that means there's a accumulation like the point. Let us say x naught inside of x. Then what we can say is that then we are able to write down our function locally as some holomorphic function minus we just translate by this guy so that this would have infinitely many zeros accumulating at x naught. So of course this f is holomorphic, local holomorphic function. After choosing some like the small like the holomorphic like the core like the neighborhood. So because so if this is not like the discrete, then we are able to find the accumulation point such that so each of the because it belongs to the same fiber so that it maps the same point so that we can just translate to make the target point to maps to just a zero. Then we know by the identity theorem identity theorem. So f must be constant near zero. I mean, f is like the um yeah capture f. This guy must be constant near like the zero. So that means small f must be constant near zero, near x naught. So once we get this guy, then by the connectedness and also the continuation, so that by just expanding this type of the open set, so f must be constant everywhere. That contradicts the assumption that we said the given holomorphic function is non-constant. So this forces that the fiber should be finite. So that once we establish this like the claim, then the fiber, because this is compact and discrete, this is finite. So that now we establish the second like the implication. So the third like the result is the numbers of ramification point must be finite, and we need to see we should establish a covering map for by looking at outside of the ramification point or the branch point. So you might already like to know that we should use this like the proposition 2. So according to the proposition 2, so all we need is so now we have already the like the surjective like the map because we already established the first like the implication F is surjective, and fiber is already finite. Fiber is already finite. So what in order to make this like the statement, in order to make this like the statement, so we just need to see why each of the two hypotheses are satisfied by this like the setting of the holomorphic map between two complex Riemann surfaces. So we also know that the point of the ramification should be also discrete. So for the third, like the implication, let us just observe that so a point x at a domain is ramified only if in a local coordinate the derivative should be vanished, which is holomorphic. So this is what we know. So and this is also the condition of the being zero of some holomorphic function. So thus, so we can say the ramification points are zeros of the holomorphic function, and we know such zeros because ramification. So it should be safe. So let me also just add one more like the line for that. So uh, thus ramification points are just nothing but zeros of holomorphic function. So we know such like the zeros are isolated. We already argued several times regarding this type of the statement. So zeros of holomorphic function is isolated by identity theorem. So if forces, because we said f is non-constant, so from here we can just argue like this. So because of that, we can say set of ramification points are discrete. And now we are done because this is in a compact set X, so that it must be finite. It must be finite. So now we already said the numbers of ramification points is finite. So let's just call those like the sets to be just a finite domain, like the branch, like the values in the codomain. Then let us just consider this like the restricted like the function. So now consider our function defined on x complement of f inverse of s that maps to y complement of s. So the reason to consider this guy is that we know that on this like the new restricted domain, f is unramified. F is unramified. So locally it is a biholomorphism, especially locally it is a local homeomorphism. So it satisfies the first condition of the proposition 2. So now this condition is okay. Now we need to see the second like the condition. We know, we know, mm, if we start from the complex subset from the codomain, if we start from the complex subset of the codomain, then the inverse image, so complex set is closed set, inverse image must be closed set, and closed subset inside the compact set must be compact. So therefore, the second condition is also satisfied for any compact K in Y complement of S, F inverse of K, this is closed in X, which is compact. That forces F inverse of K is also compact. So all conditions are now applied. So apply proposition 2 so that we can conclude F must be a covering map. All right, so now we are happy to establish the application of the previous like a proposition. Now we just leave just one more like the implication. So now let's try to say, so we assume the degree of this covering is the same as just n, and let us just say f inverse of y consists of k numbers of the like the elements. This k should be less than equal to n. So for the last implication, so let us just take any point and suppose the fiber consists of k numbers of elements like this. So because now these are part, so some of the point could be the like the because this y might be the branch like the value, so that this like the point might be ramified. So for each xi, so we are able to choose a small neighborhood. So say u sub I, in which f has a form like, so with the small core, like the small like the neighborhood and the like a local coordinate, so we can just translate to the each point center at 0, and there is a just a ramification index. So this use of I is just a ramification index at each of the this like the point. So we are able to write like this. So we know the ramified like the points are all like the isolated. So then for each nearby point, y prime, distinct from the like the given like the point of y, so sufficiently close to y, then we know the restriction u sub I delete just this like the single point is so covers its image exactly ei times. So this is guarantee. In other words, this says each like the use of I contributes exactly use of I nearby pre-image of y prime. But now we know, so it since our points y prime does not belong to S close enough to y have exactly n pre-image from the assumption and also the usage of the covering. So the n should like the covering forces that, so as long as like there are e numbers of the like the points that are overlapped, then as long as we know the information of the like the covering map, then we can simply just conclude the summation of all of them. There's no other choice other than just the n. So this is kind of the just nothing but the multiplicity after all. So that now we prove this like the statement. So now we are happy to establish this like the result because this is very like the powerful like the topological implication in the following way. We just assume, so there are two Riemann surfaces and we have just non-constant Riemann function. It turns out that outside of the branch like the points, holomorphic function behave as a covering like the map, first of all. And even there could be finitely like the ramified like the points, still we are able to handle as just a point with multiplicity. And this might be the first like the global constraint. Let me just keep the remark. This like the proposition is the global constraint on holomorphic function defined on compact Riemann surfaces. This. So this is so even locally, zeros and poles may look unrelated, but globally, compactness forces a perfect balance. That's the meaning. That's the like the meaning of like the this like the statement. So one of the like the natural like the corollary one is the following. So once we establish this like the statement, then you can now see that for each metamorphic function, of course, we assume this x to be compared with my surface, and now you know this can be simply identified as just with the same notation. It maps to CP1, so this is holomorphic. They're the same. Then we can say that the numbers of zeros of f is same as number of poles of f, of course, with multiplicities. So why we can say that? So proof is quite simple. So we know, just consider polymorphic map from x to p1 be the corresponding polymorphic function that we prove in the proposition 1. Now we have this guy. So once we have this guy, then we know that for each point, let me call by y, for each point, the number of the fiber. So this guy we know. So let's just write this guy as a say x1 to xk. Then we know. So the summation of r from 1 to k of the ramification index of each of the xr at point f is the same as the degree of this guy. Degree of this guy. Now we apply, so this is just constant. This is just constant. The degree just means outside of the branch like the point, we know the f behave as a covering like the map by just applying. So we apply here proposition 2, main proposition. And also here we also apply the main proposition as well. Then just apply this y to be 0 and infinity. Then it completes the proof. So the very like the first like the wholly is that by applying that theorem, so proposition, so there's no way to really like to split the zeros and poles for compact Riemann surfaces. So and next like the corollary is the fundamental theorem of algebra as well. Probably I should stop with this corollary of algebra. Even we already proved this like the result. So every complex coefficient polynomial polynomial has a root. Of course, we drive by the contradiction last, like in the second, like the lecture. That is, if there's a no zero, then consider one over the given polynomial. Then this entire like the function. So Cauchy estimate is this is must be contradiction. That's the argument. But now proof can be changed accordingly. So now let's simply just say so let P is the polynomial. That's the highest degree is n. Let's consider this guy. Then we can consider the information of the pole. So at infinity, so we know we are able to write this as a local coordinate by 1 over z. So we know P of z equals P evaluate 1 over W or 1 over omega. Then you can see that this is same as just this guy. So this is a pole. So you can see the infinity is a pole of order n. Then by the previous proposition, corollary one, so zero, so you can say that so the numbers of the like the total multiplicity of its zeros is also n. That means there must be zero. So this is a second like the possible like the proof of the fundamental algebra. So so then now so we establish a non-constant Coulomb function behave as a covering map outside of the branch like the point. And from here we will try to look at the like the also like the some like global constraint of the covering like the map such as a Riemann-Schurz like the theorem and so on and so on. But we are heading out to the Riemann-Rolle theorem and we'd like to reinterpret the compact Riemann surfaces once we establish the like the Riemann-Rolle theorem. So that's all for today and thank you very much for watching this video and see you next time.